Continuing on with Unit 2, and in this video we're going to focus on learning Target 4F, which is all about complex numbers. By the end of this lesson, you will be able to graph complex numbers and find their absolute value, as well as perform any operation, so adding, subtracting, multiplying, and dividing complex numbers, and simplify them to the form a plus bi, as well as solve quadratic equations using the quadratic formula and finding all solutions, including both real and imaginary solutions. So let's start talking about what complex numbers are and what this I in imaginary solutions that we're talking about. So real numbers, which we've been talking about all along, are actually a subset of a larger set of numbers called the complex numbers. And the complex numbers are based off of the imaginary unit, and the imaginary unit I is the complex number whose square is equal to -1. So what that means is that I squared is equal to -1. Since I is the complex number whose square, so I squared is meaning equals to -1. What that tells us more importantly is that I itself then is equal to the square root of -1. So up until now, anytime we took the square root of a negative number, we were saying that we got no real solution, which is true. We still don't get a real answer. But what we do get is what we call an imaginary answer, and that is in our set of larger numbers called our complex numbers. And we can do this not only for the square root of -1, we get I, but I can do it for the square root of any negative number now. So in general, for any positive number a, if I have the square root of a negative times that a, I can break that apart as the square root of -1 times a, which I could then break apart as the square root of -1 times a itself, or times the square root of a. And since the square root of -1 is equal to I, then we end up with I times the square root of a. So what we're doing here is we're replacing the fact that the square root of -1, by definition, is equal to this imaginary unit that we are using an I to represent. And of course, if a was a perfect square, we would continue to simplify that square root even more from there. So let's look at a couple examples. So in our first set, we're simplifying the following, and we're starting off with the square root of -5. We're going to use the same concept up above, where we had the square root of -a. So that -5 itself, I can break apart as a -1 times a 5. From there, I can actually break apart that square root and take the square root of -1 times the square root of 5 individually. Using our definition of the imaginary unit I, we know that the square root of -1 is equal to I, so I end up with I then times our square root of 5. And since 5 is not a perfect square, nor has any perfect square factors, we cannot simplify that anymore. And that would be our final answer there. Let's look at our second example. We have the square root of -18. We can do the same concept again, and we can break apart that -18 as -1 times 18. I can then distribute the square root as a square root of -1 times a square root of 18. By definition, the square root of -1 is our imaginary unit I, so we're replacing that square root of -1 with its definition of I, and I get times the square root of 18. Now from here, unlike 5, 18 actually has some perfect square factors inside, and on the side over here, if we think about how we could factor 18, 18 factors as 9 times 2, so what that means is that I can take out that perfect square of 9. The square root of 9 is equal to 3, so I get a 3 on the outside of the square root as well, so I actually end up with a 3i times the square root of 2 then as our final answer. Let's look at example 3. We have the square root of -12. Why don't you guys pause the video here and simplify what the square root of -12 would be equal to. So checking example 3, we can break apart that -12 as -1 times 12, and then take the square root of -1 times the square root of 12 each individually. From here, we know that square root of -1 is now equal to I, and I have that square root of 12 left. Well, just like for 18, 12 is not a perfect square itself, but it does have perfect square factors inside. So if we draw a factor tree for 12 on the side here, 12 factors as 4 times 3, with that 4 being our perfect square, the square root of 4 is equal to 2, so I can take out a 2 then, and I get 2i times the square root of 3. And we're going to want to simplify our square root as much as possible, so on 2 and 3, even though those weren't perfect squares, I could continue to simplify them even more. Let's look at example 4. Why don't you guys pause the video and try this one on your own as well. Let's check example 4. We have the square root of negative 25, which we can break apart as negative 1 times 25. From here, that would then be equal to the square root of negative 1 times the square root of 25. We know that that square root of negative 1 is equal to I, and then the square root of 25, that's actually a perfect square, and we know the square root of 25 is equal to 5. And now generally we usually write the real component first, so that 5 and then the imaginary component, just like I did with the 3i and the 2i up above. So our final answer here would be 5i then. Do want to point out I forgot an equal sign up above in example 3, so make sure we add that back into your notes. Okay, let's look at example 5 here. We have the square root of negative 5 squared. What do we think our final answer will be for the square root of negative 5 squared? Well, let's find out and check what we think it could be. We simplified the square root of negative 5 up above in problem 1. So I'm going to go ahead and replace what that is equal to, which is I times the square root of 5. We have that whole thing squared just by using what the square root of negative 5 is equal to. Now from here, let's think about what this means. I'm squaring each one of these terms, so I have I squared times our square root of 5 squared. Oops. Squared, there we go. Now I squared, we learned that definition up above, and remember I squared is equal to negative 1, and that's going to be a conversion that we're going to use quite frequently as we continue on in this section. So far we've been focusing in on I being equal to the square root of negative 1, but remember that truly comes because I squared is equal to negative 1, and that conversion is going to be helpful, and we're going to use it right here. So this I squared is equal to negative 1, and we know that the square root of 5 squared, well, the square root and the square cancel, and we get a 5 out, so we end up with negative 5 as our answer then. So on this first page here, we just practiced simplifying some square roots of negative numbers, which up until now we were just saying was giving us no real solution, which is true, but we've now learned how we can simplify and get our imaginary solution out. And I want to look at this in kind of a broader context. So at the beginning, I said that our complex numbers is what we're going to start looking at now, and that our real numbers were a subset of those complex numbers. So here in this diagram, everything inside this rectangular box here is all of our complex numbers, and on the right side we have our real numbers over here. So these are numbers that we're used to seeing all year that we've looked at. They could have some integers, so we could have 5, maybe I have an irrational number like the square root of positive 2, I could have a fraction, I could have negative numbers like negative 1/2. All of our real numbers would fall into this set. Well, we actually have this whole other set of imaginary numbers which have this imaginary unit I. So an imaginary number is any number of the form a plus bi, where a and b are both real numbers and b is not equal to 0. And that I there again is that square root of negative 1. In this part we have two pieces. The a is called the real component and the bi is called the imaginary component. And so within imaginary numbers, if our a term happens to be 0, which is our real term, then we just end up with b times I, and we call this a purely imaginary number since we have no real component to it. Just like real numbers, we can graph coordinate pairs of real numbers, we can actually graph imaginary numbers as well. And so we have what we call the complex number plane, and in that complex number plane, the point a comma b represents the complex number a plus bi, where again a is that real component and our bi is our imaginary component. So what we have here to the right looks very similar to what we're looking at before. We have an x and a y-axis. But instead of calling it the x and the y-axis, I'm calling the x-axis the real axis now. So that's representing this a component. And then our y-axis is now our imaginary axis, and that's representing the b component. So if I have some number a plus bi, I can graph that as a coordinate pair at a comma b, where a is the real component and b is that imaginary component. Now we can also find the absolute value of any complex number. By definition, the absolute value of a complex number is the distance from the origin in the complex plane. So our origin is still right where we expected it to be at 0, 0, and the absolute value is the distance between the origin and that complex number. So this purple line right here represents the absolute value of a plus bi. Now I have the definition down below as the square root of a squared plus b squared, but I want to talk about where that's coming from. So here, if I were to form a right triangle, I could actually use our Pythagorean theorem that we had from geometry. And I get this right triangle here with a leg equal to a, and then this vertical leg is equal to b. Well, we know from the Pythagorean theorem that if I take the square of each side of my leg, so a squared plus b squared, that would equal our hypotenuse squared, which we usually use that c for to represent the length of our hypotenuse if we're looking at this from a Pythagorean theorem standpoint. Well, here our c is equal to that absolute value of a plus bi, since that is the distance from the origin to our complex number. And so that's exactly why then the absolute value of a plus bi is equal to the square root of a squared plus b squared, because we would square root both sides to get c by itself as the square root of a squared plus b squared. I do want to remind you that this does not simplify down to be a plus b. If I have a square root over an addition sign, I cannot break that apart into each individual component. That only works if I'm doing multiplication or division. So let's look at some examples and see this graphing and this absolute value in action. So in the following examples, we're going to graph each complex number as well as find its absolute value. So for our first complex number here, we have 3 plus 4i, and I want us to identify the real and the imaginary parts. So our real part is the 3, that's our a value, and our imaginary part is the 4i, so our b value then is positive 4. On a graph, what this translates to is the coordinate pair 3, 4 then. So for me to graph the complex number 3 plus 4i, I want to plot the point 3, 4 on our graph. So starting at the origin, I'd go to the right 3, and then I'd go up 4, and I'd put my dot right here. So this coordinate pair 3, 4 is representing that complex number 3 plus 4i. And that's exactly how we graph complex numbers. We're only actually graphing a single coordinate pair that represents that real as the x-axis and then the imaginary part on the y-axis. Now to find the absolute value, we're using that Pythagorean theorem. So if I want the absolute value of 3 plus 4i, well, I know that my a is 3 and my b is 4. So by definition, this will be equal to the square root of 3 squared plus 4 squared, which we can continue to simplify. 3 squared is equal to 9, 4 squared is equal to 16. Adding those together, 9 plus 16 gives us 25, and the square root of 25 happens to be a perfect square, so our absolute value here of 3 plus 4i is equal to 5 then. Let's look at our second example. So if we want to graph negative 5 plus 3i, we're going to have to identify the real and the imaginary components. So our real component here is negative 5. Our imaginary component is the 3i, so our b value is that 3. Knowing this then, what would be the coordinate pair that we would want to plot in example 7? So we're looking at plotting that coordinate pair, negative 5, 3. So we're going to go to the left 5, and then we're going to go up 3, and that will be our negative 5 plus 3i. And we have now graphed our complex number at negative 5, positive 3. Next thing we want to figure out is our absolute value of this guy. So we're taking the absolute value of negative 5 plus 3i. By definition, that will be equal to the square root of our a squared, so our negative 5 squared, plus our b squared, so that 3 squared. Simplifying this down, negative 5 squared is equal to 25, plus our 3 squared is equal to 9. 25 plus 9 gives us the 34. We end up with the square root of 34 then. And in this case, the square root of 34 has no perfect squares inside of it at all, and it's not a perfect square itself, so we'll just leave that as our final answer then. Let's look at two more examples of graphing and finding the absolute value. So in example 8, we have the complex number 5i. So this one looks a little bit different here. I just have one single term, but I can still identify my a and my b. Why don't you guys pause the video right here and write down what your a and what your b is. So in this case, our a is actually 0. This is what we call a pure imaginary number since I have no real component. I technically have that 0 plus 5i then. And our b value would be the 5. So the coordinate pair we're interested in plotting is 0, 5 then. So since my a component is 0, I'm just going up 5 instead of going right or left, and I'm plotting that. In this case, I'm on my imaginary axis, which makes sense since this is a purely imaginary number then. Now to find the absolute value of this guy, we're finding the absolute value of 5i. By definition, that's equal to the square root of our a squared, which would be 0 squared, plus our b squared, which is 5 squared. Well, our 0 squared is still 0. 5 squared is going to give us 25. And then since the square root of 25 is a perfect square, I end up with positive 5 as my absolute value. Which if I were to look on the graph, I can see that from our origin at 0, 0 to that coordinate pair up there, I did go a distance of 5 units, which makes sense that my absolute value then is equal to 5. Okay, let's look at our last example of this type. We have 2 minus I. Why don't you guys go ahead and pause the video and graph this as well as find the absolute value for example 9. So let's check this together. In this case, we have 2 minus I, so our a value is going to be 2. Our b value is going to be negative 1, since I have that invisible negative 1 in front of that I. So we are graphing the coordinate pair 2, negative 1. Go to the right 2, go down 1, and I have that coordinate pair right there, representing that 2 minus I as our complex number. Now to take the absolute value of this guy, I'll need the square root of a squared plus b squared. So I'll get 2 squared plus that negative 1 squared, making sure that I have the whole negative 1 in parentheses since I'm not only squaring the 1 but also the negative. Then I end up with the square root of 2 squared is 4, negative 1 squared is going to be positive 1, so we end up with the square root of 5. And in this case, 5 doesn't have any perfect squares inside of it, so I cannot simplify that down anymore. So far we've learned how to graph our complex number by identifying the real and the imaginary component and plotting that coordinate pair, as well as find our absolute value of the complex number using our Pythagorean theorem. The next thing we're going to look at is, well, how can I add or subtract complex numbers together? Well, just like we would do for any other types of terms that we're trying to combine, our goal is going to be to combine our like terms, which means I want to combine any real parts and I want to combine any imaginary parts together. So our goal here is to simplify the following all to the form a plus bi. Let's look at example 10. We have 4 minus 3i as a one imaginary number plus negative 6 plus 2i as our second complex number here. Now from here, when I look at it, I have parentheses around each one just to identify this complex number plus my second complex number. But really, those parentheses aren't doing anything, so I can go ahead and drop the parentheses. So I get 4 minus 3i minus 6 plus 2i. And my goal here is to combine any real parts and to combine any imaginary parts. What are the real parts of this expression? So in this case, my real parts are the 4 and the -6. So when I go ahead and combine those, 4 minus 6 gives me a -2. Then my imaginary parts are the -3i plus the 2i. And when I combine those, I end up with -1i. So I just get -i then. Now that I've combined the real and imaginary parts, I don't have anything else left to combine since -2 and -i are not like terms. So that ends up being my final answer then. Let's look at example 11. So in example 11, we have 5 minus 3i as one complex number minus -1 plus 3i as my second complex number. Again, I have parentheses around each one just to distinguish the complex numbers. And in this case, we're subtracting instead of adding. Now, with these parentheses, do you think I can just drop them like I did before, or will I have to do something fancy this time? So in this case, I can drop the parentheses around the first term. So 5 minus 3i, I can drop those parentheses. But on the second term, that negative sign has to get distributed to both of these terms. So when I drop the parentheses, I just have to make sure I distribute. So I get -1 times -1, which gives me +1. Then I get -1 times 3i, so I get -3i. Now from here, my job is to combine the real parts and to combine the imaginary parts. Why don't you guys pause the video and simplify this down to the form a plus bi. So to combine these together, our real parts is the 5 and the 1. 5 plus 1 gives me 6. Then my imaginary parts is the -3i and the -3i. -3i minus 3i gives me -6i. Whoops. There we go. And since I'm already down to the form a plus bi, I can't simplify any further since I don't have any other like terms. Okay, let's look at our last example, 12. We have 2 plus I plus -4 plus 3i minus -7 minus 2i. I want you guys to pause the video and do example 12 on your own. So for example 12, I'm going to go ahead and I can drop any parentheses around terms that just have positive signs in front of them. So I end up with 2i minus 4 plus 3i. But then with this subtraction sign here, I just need to make sure I distribute, and I get +7 plus 2i then. Now from here, I want to combine all the real parts. So I have a couple more than I've had before. I have the 2, the -4, and the 7. So when I combine those together, I end up with a +5 then. So I get 5 there, and then for my imaginary parts, I have I, 3i, and 2i, and when I total that together, I get +6i. So my final answer then will be 5 plus 6i. And I am in the form a plus bi. Okay, let's look at what happens if we try to multiply complex numbers out. So now our goal when we're multiplying out, similar to when I had polynomials, if I'm multiplying numbers out, I want to be foiling and then combining like terms. So we're going to use a lot of skills that we learned in our prior section with adding and subtracting when we go to combine the like terms, but we have this additional step now of foiling. So for each one of these examples, our job is still to simplify as far as we can, which would be to the form a plus bi. Let's look at example 13. So in example 13, we have 5i times -4 plus 2i. So I want to go ahead and distribute this to begin with. I can't really FOIL since I just have a single term times two terms, so I am distributing. When I distribute this out, 5i times -4, I can multiply the 5 and the -4 to get -20 and then times I. And then with the 5i times the 2i, the 5 and the 2 can get multiplied to give me a +10, and then I times I would actually give me an I squared. Since I have something times itself again, I can rewrite that as I squared. Now, our goal was to get it to the form of a plus bi. I don't want any I squareds in there. What do you think I can do to replace that I squared? Do we remember what I squared is equal to? So I squared, we learned way back at the beginning, is equal to -1. That's the definition of what I is. since I is equal to the square root of -1, that's why I squared then is equal to -1. So I can go ahead and replace the I squared with a -1. So I have -20 times I plus that 10 still, and then since 10 and I squared are being multiplied, then when I replace I squared with a -1, I am multiplying that still to the 10. Simplifying this a little bit further, I get -20I, and then 10 times -1 just gives me a -10. Now our goal was to get it to the form a plus bi, so there we go, just flip-flopping those to have the real part first with the -10 minus that 20I. And that will be our final answer. Let's look at our second example. Here we have -1 plus 3i as one whole quantity times 2 minus 4i. So in this case, we will be foiling since I have a binomial times a binomial. So as I distribute these out, I'm going to get -1 times 2, which will give me a -2 then. Then I get a -1 times that -4i, which will give me a +4i. So we have our first terms and then our outer terms. Now for our inner terms, we have 3i times 2, which will give us a +6i. And then for our last terms, we get 3i times a -4i, so we'll end up with -12i squared. By foiling out each one of those terms, I do end up with these 4 terms here. Why don't you guys pause the video from here and combine any like terms that we can. So from here, the only like terms that I have right now is that 4i plus the 6i, so I end up with a +10i. And then for the I squared, I want to go ahead and replace it just like I did in the prior example. Since I squared is equal to -1, I can go ahead and replace that down, so I end up with -12 times a -1, which will give me a +12, so we get -2 plus 10i, and then plus that 12. From here, the last thing I can do is combine some more like terms with the -2 and the +12. So I end up with a +10 plus that 10i. As our final answer with that real and then the imaginary component. Okay, let's look at our last example. We have -4 plus I times the quantity -4 minus I. Why don't you guys pause the video right here and simplify example 15 on your own. So in this case, we're going to FOIL out again. So I get -4 times -4, which will give us +16. Then I get -4 times -I, which will give us +4i. And then with my inner terms, I get the I times the -4, so I get a -4i then. And on my last terms, I get a positive I times a -I, so I get a -I squared. From here, we can see that our inner terms are actually canceling out since I have a +4i and a -4i. Oops. So I still have that 16. The inner terms canceled, and then that I squared, remember, we can replace with a -1. So I end up with 16 minus a -1, which if I add them together, I would end up with 17 then. So in this case, in example 15, we actually ended up with a real number in the end versus a complex number. And the reason that happened is because -4 plus I and -4 minus I are what we call complex conjugates. That's going to be the last topic we talk about in this part of the video. So complex conjugates are defined to be a plus bi and a minus bi. So here our difference is that in one term I have the positive imaginary part, and in the second term I have the negative imaginary part. And the product of any complex conjugates will always be a real number, just like we got in example 15. So in the next set of examples, we're not going to solve for anything, we're just going to practice finding the complex conjugate. So let's look at example 16. So in example 16, we have -3 plus 7i, and we want to find the complex conjugate for that. Well, our complex conjugates is when the sign of the imaginary part switches. So in -3 plus 7i, the -3 is the real part, so that's going to stay the same. The 7i is positive to begin with, so in the complex conjugate, it needs to be negative since the sign will flip. So our complex conjugate for -3 plus 7i is going to be -3 minus 7i. Let's look at example 17. We have 4 plus 8i. Why don't you guys pause the video and decide what the complex conjugate would be for 4 plus 8i. So for this guy, we're switching the sign on the imaginary part, so the 4 stays as +4. Instead of 8i, we're going to get -8i then. And that will be our complex conjugate. What about example 18? We have 1 minus 3i. What would be the complex conjugate for 1 minus 3i? So in this case, our complex conjugate for 1 minus 3i is going to be 1 plus 3i. Remember that real part stays the same, so that's why I still have a +1, but I switch the sign on the imaginary part. Let's look at example 19. We have -2 minus 10i. Why don't you guys pause the video and find the complex conjugate for example 19. So here our complex conjugate would be -2 plus 10i. So again, the real part is staying the same, so the -2 stays the same, and I switch the sign on the imaginary part, so I get 10i. We're going to end the first part of learning target 4F right here with complex conjugates, and in our second part, we're going to learn how to divide complex numbers as well as solve for all imaginary and real